This is the Fung Institute Master of Engineering capstone project pitch for a swarm of unmanned underwater vehicles for underwater wireless communication. Our team consists of myself, Eric Stern, Anthony Yan, Liam Doran, and Ann Chia. Our advisor is Professor Reza Alam, the director of UC Berkeley's TAF Lab. Current wireless communication allows us to explore the depths of the universe and send data to our distant planets. Unfortunately, radio frequencies like Wi-Fi and cellular are unable to penetrate water. As such, it makes underwater communication very difficult. This inhibits undersea exploration and research. Our goal for this project was to develop a network for communication between unmanned underwater vehicles, or UUVs. Our aim was to create a communication link that can be embedded into small modular robots called CalSats. These UUVs can be linked together to create swarms of underwater vehicles, which can transmit data from deep underwater back to sea level. Our approach to this problem was to stream video between one UUV and another node at the surface of the water. Once completed, chaining multiple together should be fairly trivial. This started with a video taken from a camera that was recorded to a computer. This video is then streamed through Ethernet to another computer and played back over monitor. This picture shows our communication test setup. As shown here, the Ethernet is converted to optical signals and converted back on the receiving end. This allows different computers to send data wirelessly through different media, such as water. The idea is that these lasers can be steered towards the other receiver, which allows each side to move freely.
Thank you, Eric. While the entire laser-based communication system between two UUVs, as shown in the block diagram, can be quite complicated, I will only be focusing on the feedback control system right now, which is indicated as the yellow boxes in the block diagram. The controller involves a laser and a MEMS mirror on the transmitting end and a position-sensitive device on the receiving end. The pair of two yellow boxes in the block diagram demonstrate that a UUV is capable of transmitting as well as receiving data simultaneously. Although our team have moved on to a more robust controller with a finite horizon LQR algorithm, here is a real-time video that demonstrates the promising performance of a simple proportional controller during the development phase. We can see that the red dot indicated on the PSD jitters back to the center as the reflected angle changes. That is because the PSC records the change position and wirelessly communicates back to the controller as an input for the MEMS mirror to steer the laser back at the sensor accordingly. It is important to note that the feedback control system is two-dimensional. In other words, it is capable to steer not only left and right, but also up and down.
After having designed and fabricated a benchtop test assembly we could use to validate our optical system's tracking and communication capabilities, we then approached the challenge of integration. Specifically, for our solution to be feasible, we needed our communication assembly to take up as small a space as possible so that it would fit alongside the motors, pumps, and batteries also in the unmanned underwater vehicle. The assembly we designed is modular, inexpensive to manufacture, and sits on a set of metal rails to accommodate lenses of various sizes while maintaining tight tolerances between optical devices. The integrated communication module consists of receiving and transmitting sections to communicate to and from other UUVs. The module itself sits at one pole of the device, transceiving signals across the upper flat panel. Optical components would be controlled by computers and driver boards in the bottom pole, while hardware controlling the device's buoyancy and velocity are housed in the remaining space in the middle.
So after integrating all the components of the moving CalSat unit, we designed a fixed, wall-mounted communications unit in order to test the two-way communication between the drones. We also explored off-the-shelf and custom-designed components for hermetic sealing, which ensures that internal components are completely sealed from the underwater environment and that we reduce the number of glued interfaces, which has been found to reduce the lifespan of the product.
On account of recent global developments, our UUV fabrication schedule has been delayed, though we've devised plans for how to manufacture all of our parts once the lab reopens.
Despite the setback on the fabrication, our contribution helped accelerate the merger between UUVs and the complex swarming algorithm that TAFLab has been developing.
Once complete, the low-cost underwater wireless networking will allow for developments in search and rescue, seafloor mapping, and coral reef maintenance.
By now, we've validated our ability to send and receive information at high speeds underwater, and we're excited to continue to see this technology take hold and change the way we communicate under the sea.